Hello and welcome to my talk on statistical comparison of regression tree models on ecological grassland data. So currently there's a gap in the ecological community's knowledge in statistical methods, particularly in advanced statistical regression techniques, such as boosted regression trees and Bayesian regression trees. These techniques would be extremely useful for ecologists. They could predict what environmental conditions a certain species prefer, for example. Currently, both techniques are inaccessible to ecologists as it's pretty new to the field and there haven't been many papers using these techniques in an ecological context. This is despite both these methods being well defined amongst statisticians. This presentation will mostly focus on the boosted regression trees, as that's the method that I've done the most research on. So regression trees are also known as decision trees. They're a regression technique that involves partitioning the data in a series of binary splits. So it has the goal of finding regions within the independent variables in which the response or dependent variable has similar values. So in ecology, regression trees often aim to classify physical areas into distinct groups using information about those areas. So dependent variable is just the variable that depends on the independent variable, such as in your linear equation y equals mx plus c, x is the independent and y is the dependent because it depends on x. So a decision tree at each split follows a different path. Splits based on independent variables and the outcomes are regions in the dependent variable. The dependent variable is continuous and the independent can be either continuous or categorical. So here's an example of a single decision tree and to the right is the prediction surface, which is just another way to represent a decision tree. So at our first split, we can see that if x1 is less than or equal to t1, we go to the left. Then if x2 is less than or equal to t2, we go to the left end, finding ourselves once at terminal y2. And we can see that again on the prediction surface. If x1 is less than t1, we find ourselves on the lower area here. And then if x2 is less than t2, it's this slightly raised surface here. So boosted regression trees combine multiple weak trees, which is a decision tree that's slightly better than random guessing. And this creates a much more complex and accurate model. So each successive new tree that's added to the model aims to explain any variability that wasn't already explained by the previous trees already added to the model. The final model is a linear combination of trees, which can just be thought of as a regression model, which has each term being a tree. Multiple parameters can be used to define, and this can change the final tree. The main ones are bag fraction, learning rate, and tree complexity, and we'll discuss all of these. So the bag fraction controls the amount of randomness added to the model. It's necessary because it usually improves the accuracy and the speed of the model, and it also reduces overfitting. It's the proportion of the data to be selected at each step. So first we split our data set into our training set and a test set, which is usually about a 70 to 30% split. And then we apply our bag fraction. So a bag fraction of 0.75 means that each iteration, 75% of the data is drawn at random without replacement from the full training set, and this data is then used to calculate the next decision tree added to the model. Then we replace all the data into the training set, and we pull out another 75%, use this data to calculate the next decision tree, replace it, pull out another 75%, calculate another decision tree, until we reach the number of decision trees we want in our model. The learning rate determines the contribution of each tree as they are added to the model, and the tree complexity determines the maximum level of the variable interactions each tree can quantify. So a tree complexity of 1, for example, is a decision stump. It's got one binary split and 2 nodes. A tree complexity of 2 allows up to a 2-way interaction, so our first binary split will involve our first variable, and then our second binary split will involve our second variable. So to get these 2 parameters, they determine the number of trees in the model. A smaller learning rate is preferable, but this increases the number of trees to be computed, so therefore it's limited by computing time. So we have to play with these parameters because some of it depends on the variability of the data and also how good the regressors are as predictors. And also we have to strike that balance between the preferable small learning rate, but also not inflating our computing time too much. So both the boosted regression trees and the Bayesian regression trees can be applied on the same types of data. So this is just a quick overview of Bayesian regression trees. They also combine multiple weak trees, just like boosted regression trees, but they rely on an underlying Bayesian probability model to build each of the individual trees. So Bayesian models include a prior probability component, and this is imposed on each individual tree, and it's manipulated to control the individual tree effects and keep them small because, again, we want the individual tree effects or learning rate to be fairly small. So both methods are fairly well defined and tested in statistics literature, but we don't really know much about them in the context of ecological data. So we don't know the differences between the results of the boosted and Bayesian. We don't know the range of the attainable results, and we don't know of their relative limitations. So my goal is then to compare the range of obtainable results in both the boosted and the regression trees. And I'll do this by testing various values of their respective initial parameters on ecological data sets. I'll be using 2 data sets analysed in Cath et al. In 2017 to compare the performances and sensitivity of the regression methods. Cath was one of the first papers to actually use the boosted regression trees in ecological data. So as for hypotheses, the research they've done so far indicates that for boosted regression trees, a bag fraction of between 0.5 and 0.75 will perform best, and that the greater the tree complexity combined with the slower learning rate will result in better models and lower residual deviance. Currently it's unclear if either boosted regression trees or Bayesian regression trees will be preferable for ecological data, or if one would be preferable at all. So far I've conducted some preliminary tests on boosted regression trees using the R package Dismo with the Anguilla trained dataset, which involves a particular species of eel. So it's got some presence-absence data for this eel and a bunch of other environmental variables. This is not the dataset I'll be using for my project next year. Again, that's the Cath et al. Grassland data. So I ran a bunch of models on this eel dataset with various combinations of the bag fraction, the learning rate, and the tree complexity. So I ran bag fractions of 0.3, 0.5, and 0.8, and a learning rate of 0.005, 0.01, and 0.05. The tree complexity, I also ran values of 2, 3, 5, 6, and 8. The green models ran, but the models in red didn't. And this is most likely because the combination of the high learning rate and the high tree complexity would have resulted in models that had very low resolution and wouldn't have been very useful. So the package just refused to run them. So here is the number of trees and the residual deviance that each model resulted in. So you can see as the learning rate increased, the number of trees required decreased, and as the tree complexity increased, the number of trees required decreased as well. Our optimal combination of a low learning rate and a high tree complexity resulted in the lowest residual deviances. Low residual deviances mean that these models were a better fit, but we don't want a more complex model unless the reduction of residual deviance is worth it. So it's a bit of a balancing act between getting a simple model, but also reducing the residual deviance as much as possible. So here I've plotted the fitted functions for the 6 most influential independent variables for Model T. Model T had a bag fraction of 0.5, a learning rate of 0.005, and a tree complexity of 8. So these fitted functions, they can be used to interpret the model that was produced. So for example, you can see in this first graph here that the eels preferred places that had a high summer air temperature. They also preferred areas that had a high deforestation of indigenous forest, and they preferred to be close to the coast, although they did penetrate fairly far inland. Additionally, you can see that the electric method of fishing was the most successful, and that the eels preferred places that had a high proportion of rainy days. And they also liked places that had a very slight slope. So next for me, I'll be continuing my preliminary analysis and exploration of the boosted regression trees. And I'll also be starting my initial analysis of Bayesian regression trees. And then next year, when I begin my project, I'll do the comparison analyses between the 2 methods on the grassland data. Thank you for listening to my presentation. I hope it was interesting.